Hello, this is going to be a just kind of a informal video where I talk about math and physics. Um, it'll probably end up kind of long and kind of rambly. And just I don't have any coffee in front of me. I happen to have Pepsi, which is really bad for your health. But um, yeah, just pull up some coffee, pull up a pen and a paper, and chill. Let's talk about math and physics a little bit. So I I work as an engineer in a lower engineering role where I'm able to have the position without having the degree due to some strange life circumstances and stuff. Normally, people have a degree in electrical engineering to have the role that I have. Sometimes they just have an associate's degree, which I don't technically have, but I have like enough courses that I think if I went to go apply for it, I could just probably take 2 courses and they would give me the degree. Um, I just didn't finish it. So anyway, there's a little bit about that. And I think though what I want to focus on in this video is kind of the bridge between math and physics. So I'm a little bit older, um, but I've done a lot of classes. I should have looked it up so I'm not inaccurate, but it's probably like somewhere around 150 to 180 credit hours that I have, and I have a completed degree in biblical studies, a bachelor's degree, but I've also studied, um, like, been enrolled in other programs as well that I just didn't finish, several of them, because I just love to learn. To be honest, I think if I were to pick my ideal major, it would probably be philosophy because it kind of touches on everything. Uh, anyway, all that aside, so I I've always been really good at math. Like not like A plus good, but solid B plus good without even trying. And if I put in a little effort, I can get A's. And I've been that way my whole life. In high school, actually in elementary school, one of the first compliments I ever remember receiving was in, I think it was first grade actually. My teacher told me that I was really good at math, and just always from there on. But I never applied myself. I would sleep in math class and get A's instead of like apply myself and be able to actually do something meaningful with it. So contrast that with physics. I took advanced physics in high school, probably because, like I said, I'm good in math, so I was able to get into advanced physics. And I struggled. I had a really, really hard time. Um, it's been years, but I think I probably got a B, maybe like a B minus or something. But I remember struggling to get that B, which was very unusual for me in a math class, where because physics is mostly math. Um, some other subjects I'm not so good at, right? Like I failed English. I'm not very good at languages, which I love languages, but I'm not really good at them. But math I've always been good at. Physics, though, for some reason, I can't figure it out. Even though it's mostly math, I'm not very good at it. And so fast forward to the future, after I completed, well, actually, I had to take one class in my biblical studies program. And then after that, I took a couple of math classes. I don't know what I just said. I took one math class in my biblical studies program, and then afterwards I've taken a few math classes, and the same thing applies. I mean, I get annoyed if I don't get 100% on a test, because I can usually do that, with the exception of differential equations, but all the other math classes I've taken have been pretty much the same, and I've only got one class left to go for the core math classes required for the electrical engineering program that I'm enrolled in now. So, however, with the physics classes, it's the same. It's the same as it was in high school, and I just struggle. Like I struggle so hard to get a B, and at the end, I just feel like I don't get it. They throw these questions at me. I feel like I don't know what to do during these questions, and so yeah. So anyway, that's kind of what I want to. But on the other hand, though, the part of math that I prefer is the applied mathematics. So you can sometimes math gets into number theory, uh, prime numbers, the Riemann hypothesis, and all these different kinds of esoteric type things topology and um, anyway, these things interest me a little bit, but more like to where I'm cool with watching a YouTube video on it, but I probably don't want to take an actual course on it, and I don't want to sit down and spend hours working out the problems. But when it comes to more applied mathematics, so calculus, math where you feel like you have real world problems, I love doing it. I enjoy it. I could probably sit down and do it for fun. It feels almost like a video game to me, I guess. That same kind of, I have this problem. I want to conquer it, and when I get done, I feel that little rush of uh, maybe endorphins, whatever it is, that the chemical that your brain gives. Uh, so I like it, but at the same time, physics is where that happens the most, and I struggle with these physics classes. So I think for me, the problem is that I don't memorize well, and mostly in math, there's not a lot of memorization. Some exceptions include trigonometry and calculus. There's a lot of relationships to memorize, but still, it's a very small amount compared to the amount of stuff you have to memorize in physics. To be honest, I think that's probably my main issue is I'm terrible at memorizing. So anyway, let's just uh, let's just try to do some physics and math here. So let's say that so uh, you have I also think so when I was learning physics, I really think that I wish they would have started. I guess I don't like how physics tends to be taught in a way that is messy. I don't learn very well from messy presentations, which is funny because I'm giving a messy presentation, but I don't learn very well that way. I need a nice, you know, tight, uh, where everything fits together, harmonizes, where all of the contingencies are explained, where there's no, loopholes in the explanation. I need that kind of explanation, otherwise I don't learn very well. Mathematics tends to provide that. Physics doesn't. In physics, I've noticed the common theme is that their teaching style tends to be very messy, I guess, which is nice because the real world is like that, but I have a hard time learning that way. So if I were to go back and uh, learn physics again, I think I would prefer to start with just, I think it tends to be taught in more of a historical way. So, for example, they say, well, let's see, they say they want to go over, let's not use that, that's too skinny. They want to go over kinematics. And actually, so I've noticed, I recently took Physics 1, and my little brother also is now taking Physics 1. I've noticed that there's a huge difference in the order that things are presented and the things that are focused on, because physics covers a lot of topics. So I think that's kind of stands to support this idea of what I mean when I say that it's taught in a way that's messy. Just the fact that you can do it in any order, it is a little bit unnerving for someone like myself, I guess. So, but the order that I went in was kinematics, then we had Newton's laws dealing with forces, and combine this with a couple things. So we dealt with gravity, projectile motion, then we added friction, and what else? I think there was something immediately after this, but maybe the next thing was it started to deal with orbits. I think before that we dealt with torque. Oh, work, that's what I'm missing. Energy and work. Oops. And then we dealt with universal gravitation. I think those are all the main themes. I'm probably missing something. Gravitation. Now that's physics 1. You can see this. Physics 2. Oops. We have been going over. I actually just now had to drop this class. I plan on retaking it because of some issues that have nothing to do with the class due to an injury, basically. But in physics 2, we started with charges and Coulomb's law. Then we dealt with capacitors. And then circuits. First we did, just capacitor circuits. Then we did resistor capacitor circuits. And next we would have done resistor capacitor inductor circuits. And after that, what were we going to do next? I don't remember. So, but for me, this is what interests me more because I like electricity. Mechanics does not interest me very much. It's kind of cool. It's the same as the higher level math. I like to see it, but at the end of the day, I don't care to know how to do the problems. But circuits and electricity, those are problems that I want to know how to do. So for me, I would have rather have focused in physics 1 on universal gravitation because universal gravitation and Coulomb's law pair together. So I would have rather have dealt with F equals G M1 M2 over, should be R squared, I'm pretty sure. It's the same. So this is the force of gravitation. Instead of saying force equals usually mass times acceleration, which acceleration is g, force equals mg. Usually we used this form. I guess you have to because this deals with two masses, and I don't believe this g is acceleration, whereas this g, little g, is acceleration. So you kind of have some parallels. Actually, you have some direct parallels to both now that I think about it. So in electrical physics, what they say is the electric force equals K times charge 1 times charge 2 over top of the distance squared. And these are basically the same. The difference is we're treating charge as mass, and the constant is different. K is a constant and G is a constant. And then this is the distance between the center of the two bodies squared, or this would be the center between the center of the mass, and this would be the center of the charge, but otherwise it's still center. And then we have another formula, which I believe it's force electric equals the electric field times the charge. Fairly certain that's right. This can be a vector, this can be a vector, this can be a vector, this can be a vector. Technically that's a vector anyway. So yeah. So these also parallel, whereas, except I should have wrote QE, whereas this G compares to the electric field and M compares to the charge. So there's a very direct parallel. And let's see if I should explain what these mean a little more. this is the universal gravitation formula, and I might mess this up a little when I'm explaining it because this part of the class didn't interest me at all. I don't care about astronomy at all, it just doesn't interest me. So but as I said, it parallels the formula um, with electric force, which I do understand a lot better and does interest me. So I think I can do this correctly. So let's say we have two bodies. Here's a mass. Here's a mass, m2. And we have some distance between the centers of the masses. So if we want to find the force of gravity that these two are exerting on one another, this one has a really tiny force going this way because it's being pulled by a smaller mass. This one experiences a very large force this way because it's being pulled by a much larger mass. And if we want to find this force, something's not right there because we have two. Are those equal forces? Yes, they are equal forces. My mistake. They're equal forces. The accelerations are different. So this one experiences a force in this direction. This one experiences an equal and opposite force in this direction. And this is Fg. This is Fg. So if we wanted to calculate that force, we could say the force of gravity equals g, which is a constant, you can look it up, times mass 1 times mass 2 over top of the distance between the center of the two bodies squared. And for charges, it's basically the same. We have, this could be a charge, this could be a charge, this feels a force this way, this feels, it should be an equal and opposite force this way. Force electric, force electric, and this is some charge. There's some charge value here, and there's some charge value here, and there's a distance between these two bodies. So in this case, we say that the force, the electric force, equals charge, that's the constant, equals this Coulomb's constant, times charge 1 times charge 2 over top of the distance between the two bodies squared. The difference though, for mass, the directions always point as shown. For charge, the directions point as shown if the charges are opposite, but if the charges are the same, then the directions point outward, away from one another. Otherwise, the calculation is completely the same. So this is electric force, electric force. This is R. This is still Q1, Q2. So technically, this should have absolute value sign. So the force electric, the magnitude of the force equals K times the magnitude of charge 1 times charge 2 over top of R squared. And this will tell us the magnitude of this force electric. And then to know the direction, whether they point inward or outward, you pay attention to the signs of the charges. So there's a strong parallel there. Now the parallel between the electric force and the gravitational force in this regard is going to be, so let me get some space. Actually, where do I want to delete? Let's just delete this here. Okay. So if we have, let's say that we have this this tiny little asteroid here. This should be Earth. Let's make this Earth, which means we'll make it really big. Let's say this is Earth, and this is a person. Let's make him jumping. Falling, how about that? This is a person falling towards Earth. So they're falling right now, so their velocity is in this direction. Their acceleration is in this direction. And there's a force moving them in this direction towards the Earth. So in this case, force equals mass times acceleration. And that's nice to know because this form can be used for many different types of forces other than just gravity. So this force could be this equation would be applied to a pushing force. So if you had a door and you're pushing on the door, then the force would equal, well, how about, let's say, a box sitting on a frictionless surface. So if you had a box sitting on a frictionless surface and you push the box directly horizontal, you're pushing forces in the same direction as the force of motion, then you would say that the force of push on that box equals the mass of the box times the acceleration of the box as you're pushing it. So that's what this form means. For this problem, as I set it up here, we say that the acceleration is g, meaning little g. Force equals mg. And the sign here is actually just based on your setup of the problem. So if you want to say that the upward direction is positive and the downward direction is negative, then you would say that the force equals negative mg. But you could alternatively make the negative the top and the positive the bottom, and in which case this would be F equals positive mg. So yeah, so this is what this formula means. And this is the force of gravity acting on this person. And the force of gravity is the mass of the person times g, which is just the acceleration constant for an object close to the surface of the Earth. Close meaning not outer space, basically. So yeah, so now let's take, what about this other force electric equals the electric field times the charge? So in this case, we have so in this case, the direction, the object is moving downward. So I want to keep this also with a downward force, just for simplicity's sake, because with electricity it can flow in either direction depending on positive and negative charge. So in this case, if we want the force, so this is, my lines here represent the electric field. And the force is going to move, I want the force to move this way, I want the electric field to move this way, just because I want it to do that. You could do it the other way, but I think the parallel between these two setups will be more apparent. If I have the electric force going down, the electric field going down, which means that the electric field always goes from the positive charge to the negative charge. So this is a positively charged plate and this is a negatively charged plate. And then there's a charge in here, but if I have this be a negative charge, it's actually going to flow, it's going to push upwards. The force will be upwards because the electric charge always moves against the electric field, whereas the positive charge always moves with the electric field. So in this case, we would have, I guess you could say acceleration, we'll say force. So there's a force pushing this proton or whatever positive charge I happen to have there towards the negative plate. And in this setup, the electric force is equal to the electric field times the charge. So there'll be some value for this charge in coulombs. I should have included units in these explanations, but alas, I did not. So there'll be some some value for this charge. There'll also be some value for the electric field, which the formula to calculate the value for the electric field, I think you just use this formula. I can't remember. I don't remember learning a second formula. Maybe I forgot it. So you could say you already knew the force. You could say the electric field equals force divided by charge, for example. But let's say you know the electric field and you know the charge, you want to know the force, you could use this form. If you know the electric field, sorry, if you know the force and you know the charge, but you don't know the electric field, you could use this form. And obviously by extension, if you didn't know the charge, but you knew the force and the electric field, then this would tell you the charge. So there's some comparisons between dealing with the force of gravity and dealing with the electric force. What else do we have? We also have work in both of these situations. So gravitational energy is preserved, is conservative, and electric energy is conserved. It is conservative. So the energy gravitational is conserved. The energy electric, let's use a small e, is conserved. Now, what this means is so the total energy in the system is going to be the potential energy plus the kinetic energy. So the potential energy initial plus the kinetic energy initial equals the potential energy final plus the kinetic energy final. And this is dealing with gravitational energy. I just didn't write G's for all those. The same is true for the electric system. The potential energy electric initial plus the potential energy kinetic initial. Sorry, kinetic plus the kinetic energy electric initial equals the potential energy final plus the kinetic energy final. And in this case, if I remember correctly, potential energy in a gravitational system is mgh pretty sure that's correct. Let me look that up real quick. I'm not 100% sure on that one. Where's my mouse? Yeah, mgh. Okay. So this is the mass of the object. So if we go back to our object over here, the mass of this person times g, which is the gravitational constant for a body that's close to the Earth, times h, which is the height of the object from the Earth, plus the kinetic energy. Kinetic energy is 1/2 mass times velocity squared. And in this case, this will be a velocity initial. Mass doesn't change, initial or final. And in these types of problems, we're considering that mass is constant, just like because it is, mass is constant. And this is height initial. This is equal to potential energy final is mgh final plus the kinetic energy, which is 1/2 mass times velocity final squared. So this then is how you can solve energy problems, and often some things in here cancel. So for example, in this diagram that I set up on the left here, we're assuming that he's falling at the start of the problem. So the potential energy initially is 0 because he is in motion already. So there's no potential energy on the object, which is the person. So it's all kinetic energy. Then the final energy, if I didn't actually set the final conditions, but let's say the final conditions is him going splat into the earth. And in that case, the kinetic energy will be 0 because he is no longer moving. And it will all be potential energy, but actually we'll find that his potential energy is also 0 because the height, if he hit the earth, typically you would say that the height is 0 at that point. If you didn't want to consider the height 0 at that point, then the potential energy would not be 0. But I think most people, when they would set up this problem, would include the height to be 0. So our new formula is 1/2 mass times velocity initial squared equals, something tells me that's not right because this can't be 0. You know what? I don't think this does go to 0. Maybe that's not actually the final height. This does go to 0, but this may not be the final height. I'm gonna leave a question mark there. So 1/2 mass times velocity initial, I know that part's correct, squared equals mgh. It seems that this only works if you consider the starting height. So I would need to relook at this. I didn't actually do very well in this part of the class. So anyway, this part I know is correct before I started crossing stuff out, and this part's correct. Because over here, when we look at the electric system, these ones I did a little better with, and they're almost the same. So the potential energy here is not mgh, it is, I think it's k q1 q2 over r. Or is it just k? I'm pretty sure that's right. So this is the potential energy. And you'll notice it's almost the same as the formula up here, which is Coulomb's, whatever, Coulomb's law, Coulomb's formula. I think it's called Coulomb's law. It's almost the same except r is squared up here. R is not squared when you're dealing with the potential energy. And the kinetic energy is the same. Velocity initial squared. And then, so this should be, R should be initial, K, Q1, Q2 over R final plus 1/2 mass times velocity final squared. And for this one, let's say that we have these two charged bodies. Let's say this one is positive. This one is a much larger charge, so that I'm not meaning this to represent mass, but charge. So this is Q1, it's very small. Q2 is a very large charge. And then let's say that Q1 is moving in this direction with an initial velocity. Q2 is not moving. And at some point, Q1 will stop right here. And we want to find this stopping point. That means that this R here will be R final, the distance between the two. So now if we set up this one I know how to do because I was practicing this. Initially, our potential energy is 0 because this is our object that we're dealing with. The energy of this object, and initially it is moving, so it's all kinetic. So this goes to 0. Our final position, we consider it stopped, so our kinetic energy final will be 0. So now what we're left with is 1/2 mass times velocity initial squared equals k, which is a constant, times q1 times q2 over top of r final. This one I know is correct. I'm not sure what mistake I made over here, but this one is correct. And in this case, now you can solve if you're only missing one of the variables here, then you can solve for the one that you're missing. Plug in and solve. And so we have the charge on the small object, the charge on the large object, the initial velocity, and the final distance between the two objects. As long as you're given, how many are there? 1, 2, 3, 4, 5. There's 5 different variables there. Remember, k is a constant. 5 different variables. So as long as you're given 4 of the 5, you can solve for the one that you're missing and figure that out. And I guess that's enough for this video.